asking.
Okay, all right. So, what is replication? You repeat the same experiment in more than one experimental unit, which is called as experimental unit. Replication, right? The purpose of replication is to obtain the error variance. The purpose is to obtain the error variance. So why error variance is important? In this experimental design, why the error variance is important? Anyone? Why the error variance is important? Darshani? You are free to answer, no problem. Darshani? Indujalini? No, I'm just asking the questions from what you have learned. What is the purpose of error variance? Because we said we want to replicate a treatment. So using the replication, you obtain the variance. So what is the definition for error variance? Anyone? These are some of the questions which has been appearing in last quizzes, last year quizzes. I don't know. Last year quizzes, some of the questions. What is error variance? Anyone? Peony? Latsika? Just tell whatever the answer, doesn't matter. I'm not going to blame anyone. Madhusha? Subhanki? I'm reading the names appearing here. What is error variance? If somebody, because replication is done to obtain the error variance, that is fine. So what is, how we can define the error variance?
If we apply the same treatment to 2 or 3 samples, that also vary among each other. That is due to the error variance.
Right. That means if somebody asks what is error variance, right, you should be able to answer what it is. It is the variance between the units, variance between the experimental, I will put it as EU, not European Union, experimental units. Error variance is the variance between the experimental units, plural, several units, right? Variance between the experimental units, which are treated similarly. Which are treated similarly. So here, which are treated similarly mean they have been treated with the same treatment, right? So for example, let's say in my case, I have T1, 3 units of T1, right? 3 units of T2, and again 3 units of T3. Now I can calculate the variance. I can calculate the variance within treatment. I can calculate the variance within first treatment, within second treatment, within third treatment. So I can calculate the variance between these 3 units, between these 3 units, between these 3 units, right? So that is called as the error variance. Error variance from treatment 1, error variance from treatment 2, and the error variance, let's say x, y, z. So as a cumulative, so the error variance is given as x plus y plus z. We give in a cumulative form because it goes as a one experiment. If the variance between the experimental units which are treated similarly, that is called as error variance. So we calculate the error variance for first treatment, error variance for second treatment, error variance for third treatment. Right. Now, what is the purpose of error variance? I could remember I have taught this in your first course also, under the regression, if you can remember. Did I talk regression? Tanaumar, did I taught regression? Yes, I did teach regression. I think I can remember. Tanaumar, are you there?
Yes, sir. Yes, sir. You talk.
Yeah. Did I talk? I mean, did I taught you on regression? Or
Yes, sir.
right. Okay. Because I can't remember, so that's why. Right. So in the regression also, I have mentioned this error term for the first time, right? So can someone tell me why this error is important? Why this error variance is important? So we said what is error, how we can define the error variance, and why it is important. Any reason? Because can you remember in our test or any testing? So the first step is formulation of hypothesis, right? Second step is test statistics, right? What is the third step? Sarah, what is the third step in any testing? I'm recalling what I have taught you earlier. Sahara, Kirija, Ola, silent, huh? Vidushan, Vidushan. Tell me what is the other step, other two steps? Varagunan, Mafra. No one is there in the class, huh? It's look like. You'll have to answer, huh? Please. Right. Varagunan, Mafra. Interesting. Subhanya. No one is in the class, it look like, huh? Right. Yeah. Kirija?
Decision making, third step, and fourth step is conclusion.
Okay, good. Decision making. All right. This so in any test, this is important. Even in design, these four steps are there, right? And conclusion. So in any testing, when in design, we are doing testing, right? So in any design, even design or any testing, we should have these four steps, definitely. Right, now, look at here in design, when you talk about this test statistics, actually in design, test statistics is based on F distribution, right? It's based on, I will write it as F distribution. So F distribution is depend on explained variability divided by unexplained variability. So this unexplained variability is the one we call as error variance, right? So this is the test statistics these are the test statistics in experimental design, right? So we will come to that later if we have not done. So you see, this is distributed with F distribution. I have already introduced this distribution in your first course, right? So basically what we are looking for, our calculated value of F, which is based on the explained variability divided by unexplained variability. So basically, in a design, these two, explained and unexplained variability, are actually, this is the variability due to treatment variance divided by error variance. You see, this is our test statistics. So that means we have two components, numerator component and the denominator component. In the denominator component, we have error variance. We are comparing with error variance. So that is why we need the error component. We need the error component. That is called as pure error. Pure error. So this pure error is not due to any facts where we don't know the reason for this pure error. So that is called as pure error, right? So this is due to no any mistakes in the experiment. This is due to some pure error, which cannot be explained, right? Which cannot be explained. Only God knows what is the difference between these two objects, which are treated similarly, right? Everything is similar. Management, variety, treatment, everything is similar, but still they produce different values, right? So if you measure the variability, which is called as the pure error or the error variance. So this error variance is important. Why? Because we want to make a decision based on test statistics. So this test statistics is the calculated value is based on the variability or the ratio between these two variables. One is explained variability, the other one is unexplained variability. So that is why we need this error variance. Right? The third principle, control of unexplained variability. So we want variability, error terms, which is true variability, where sometimes this variability can be accumulated. For example, let's say if you have the total variability, right? If you take the total variability, this is total variability. If you have the total variability, so part of this variability can be explained by treatment. This is due to treatment variability, right? This is due to treatment variability. The remaining is called as error variability, or we also call as residual variability. So you see here, here we need the residual or the error variability, of course, but unnecessarily, we don't want to increase the error variability. Error variability should be there, but that error variability due to pureness, pure error which we cannot explain. For example, look at here. Now, I want to do a germination test. Germination test on red lady. How the red lady are in the red lady variety? Red lady. Can you tell me what variety is available on red lady? Anyone?
Papa.
Papo, right. For example, red lady, I'm going to do a germination test. What is the hormone that use to induce the germination? என்ன ஹோமோன் பாவிக்கிறாங்க මොනවාද ஹோமோன் පාවිච්චි කරන්නේ අපි germination වැඩි කරන්න auxin, right? What is the market, what is the auxin in the market? What is the trade name? Anyone? I'm asking some difficult question in agriculture, right? Agriculture department people, are you there? I have the name list. Then Kiavanda Isra, you'll have to tell. Huh? Indole acetic acid. Is it available in the market as indole acetic? Because I don't know. That is why I'm asking. Root-on, that is usually applied after germination or before germination? Before germination. Right, okay. Whatever the hormone, right? Let's say root-on. As an example, sometimes we don't use root-on to papo, but I'm talking about how this variability, what is the problem this variability, right? I'm going to test with root-on on the variety red lady for the germination test. So I'm taking root-on, different concentration, 1%, 2%, 3%, 4%, and 5%. I have 5 treatment. Treatment 1, treatment 2, treatment 3, treatment 4, and treatment 5. So I'm considering these are the treatment. These are the treatments, right? Now, before I apply this treatment, what do you need before I apply this treatment? There are 5 treatments. So we want to germinate. Let's say this is a Petri dish, right? So there are seeds, papo seeds. Let's say I want to each treatment replicate 3 times. So how many experimental units do I need altogether? How many experimental units do I need
50.
altogether? Pardon?
15.
15, yes. So likewise, you need 15 experimental units, right? Because each treatment, you are replicating 3 times, right? So let's say each Petri dish consists of 25 seeds. So how many seeds do you need? Oh, 50 seeds, I will say 50 seeds per Petri dish. So how many seeds do I need?
750.
150 seeds. I need 750 seeds. What is the best way to obtain the seeds? What is the best way to obtain the seeds? Anyone? என்னன்னு நாங்கள் இந்த 750 විදිය எடுக்கலாம். කොහොමද අපි මේ බීජ 750ක්ම ගන්න පුළුවන්? මොන ක්‍රමයකින්ද අපි ගන්න? You can answer in any language. So I try to bring this experimental error. Anyone?
ஒரே பழத்துல இருந்தே சீட்ஸ் எடுக்கும்.
Good. ஒரே பழத்துல இருந்து என்ன எடுக்கிறது? 750 சீட் வரும். So he said we can obtain all these seeds from one single fruit. Whether it is possible to obtain from one single fruit. Let's say we cannot obtain from one single fruit. So what is the other option?
Obtain from same tree.
Same tree. Yes, good. Try to obtain from same tree. Why is that? Because if you are unable to obtain from one single fruit, because we cannot obtain from one single fruit, the reason is we'll have to have very uniform size of good quality seeds of 750. So we'll have to have equal type of seeds 750. So in a papo, when you cut the papo, some seeds may be white in color, some seed may be mature. I don't know how many of you have seen after cutting the papo, right? So the quality differs. If the quality differs, that is, you cannot compare these seeds, because some are very good quality seeds even within a single fruit. Some are very bad seeds. Bad means they are not ready for germination. So already we have a problem. So before we applying the treatment, already there's a variability among the seeds in terms of germination. So can we carry out this before applying the treatment? No, that is wrong. So that is the name of the experimental unit. Experimental unit are the units where we measure the response. Meantime, all the experiment units should be same in terms of quality, right? So here we could think about only one single fruit, or we can think about several fruits. Take, this is not papo, let's say tomato, for example, or go for another type of fruits. So these are some of the problems. Sometimes, without knowing these facts, because we need only 750 seeds, that is fine. If you need 10,000 seeds for experiment, for example, what to do? Right? We cannot obtain from one single tree. We'll have to go for several trees. So you see already some variability is there. So we want to reduce the variability as much as possible. So that is called as unexplained variability, right? So we want to reduce the unexplained variability as much as possible. So whatever the variability that we can explain, that remove that. So that is the basis of unexplained variability, or the reduction of unexplained variability. What is happening if the unexplained variability increases? Look at here. If the unexplained variability increases, what will happen? Anyone? This on side. If you increase the unexplained variability, what is happening? You see this, right? This portion will increase. This portion will increase. So that if this portion increases, what will happen to the F calculated value? Anyone? What will happen to the F calculated? Yeah, F calculated value will be reduced. So if calculated value reduces, what will happen? If calculated value reduces, what will happen? Look at the F distribution. F distribution is a distribution like this. It's a skewed, right skewed distribution. We have introduced that in our first course, no problem, right? So this is the F distribution. So now there is the 0 to plus infinity F distribution. Let's say this is your alpha value, whatever the alpha that we are taking. So this is called as critical value. Let's say this is given as F table value. So this area is called as, how do we call that area? The marked area? Rejecting region. The marked area is called as rejecting region. The unmarked area called as non-rejecting region. Unmarked area is called as non-rejecting region. So what will happen if my calculated value coming smaller and smaller? Anyone? If my calculated value is smaller, chance of rejecting will be increase or decrease? Rejecting my null hypothesis. Tivagaran, Sri Tivagaran. Reduce. Chance of rejecting our null hypothesis will reduce. So this is one of the problems. Even if there is a treatment effect, sometimes there may be a treatment effect, but it will be masked by this error term, because if the error term is increases, right? If the error term is increases, what will happen? Definitely the area if the error term is increases, definitely the calculated value decreases. If the calculated value decreases, the chance of rejecting our null hypothesis will go down, even though if there is a treatment effect. Even though actually there's a treatment effect, the chance of rejecting goes down. So we end up with the result saying there is no treatment effect. Even though there's a treatment effect, we come up with the conclusion saying that no treatment effect. So no use of that experiment. You see, even after putting all the hard work, finally we come to a conclusion, no treatment effect. So what? So this is the problem with the error terms. So we'll have to control all the error terms, all the possible error terms. We'll have to separate all the possible error terms. So if you take, for example, seeds, as a planting material for the experiment, and meantime, if you take cuttings or clones, what do you think? Where we can reduce the unexplained variability much more? Is it among seeds, or is it among clones or cuttings when you do the experiments?
Cuttings.
Cuttings, the unexplained variability is reduced. Yes, less. Why? Because it's coming clones, cuttings, they are coming from the mother plant. So they are same character as the mother plant, right? But in seeds, there may be a variability. So you see, this is how we can reduce the variability. Right. I will point out one more point and then we will. Yeah, I have already taken some time. Yes. What is the principle of CRD design? Where we can apply CRD design? Under which circumstance?
More uniform.
More uniform. We call it as. homogeneous condition. Give an example for homogeneous condition, couple of examples.
Tissue lab or laboratory.
Yeah. So usually if you take the laboratory, the condition here, 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 all are same more or less, right? Laboratory, plant house, net house, all these we can assume that the environment is more or less homogeneous. So that we can apply this, right? So you have seen, you have already learned, I just recalling. What are these? Don't worry about different rotations. So you might have seen a notation like this. What do you call this? Observed value, right? This is called as model of CRD. CRD. When you formulate your ANOVA, these are the components that comes automatically in ANOVA, right? Let's say this is an observed value of ith treatment, jth replicate. You have learned this, right? Tanish Kumar, படிச்சீங்களா?
sir.
Right.
Yes, sir.
Okay. So here, this is a grand mean. This is the ith treatment effect. Right. So this is the random error of ith treatment, jth replicate. Treatment, jth replicate. Right. So that is the model for CRD. CRD we apply in a homogeneous condition. I think you have already learned and did a lot of examples on that. Any questions on that? Because everybody should understand all. Then only we can go further. Yeah. Anybody has any questions on that? Right. So basically, you see, as I said, in the ANOVA, analysis of variance table, ANOVA table, right? Analysis of variance. That is the meaning of ANOVA. So that you see, these two components comes. Source of variance, right? Here we have treatment, error, and total. You see, this is due to treatment, that is there. This is due to error component, that is already there. So by looking at the model, we will be able to see how many components are coming in the ANOVA. Right? Then total is actually addition of these two. Addition of treatment and the error. So you have already seen that. Right? Right. Yeah, the second design, RCBD. What is the difference between CRD and RCBD? The first design, CRD. The second design is RCBD. What is the difference between these two? Very quickly. What is the difference?
Yeah, variance.
Pardon?
It's the heterogeneous condition, variance of this.
Yeah, if the experimental site is a heterogeneous, give an example.
Agriculture field.
Agriculture? Agriculture field. Yeah, good. Agriculture field. For example, let's say I have a gradient. Okay. So how I would say, there's a river. There's a river or channel, water channel goes in an experimental field. Now, what is the problem in this? This is my experimental area. This is my experimental area. So what is the problem here? Anyone? If you consider two places, let's say A, B. What can you say about these two positions? Moisture level, where the moisture is high in the soil.
They contain more moisture.
A contain more moisture than B. So how do we call this phenomena? A has more moisture, B has less moisture. So this is one example. Similarly, in the field, we may get one area may get higher fertility, the other area may be less fertility. For example, in a slopy land, the land is slopy. I'm going to do an experiment. So here A, here B, where the fertile, which one is high fertile, A or B in a slopy land?
E.
A is having more fertile than B because of the erosion, bring all the nutrients down, right? So likewise, there's a variability already, it's heterogeneous condition. So in this heterogeneous condition, right, we could bring into smaller units which are homogeneous. That concept is called as blocking. So now what I'm going to do is, I'm going to block this, right, into 4 blocks. So now you see, if I say C, what do you think about C? Site C and A. What do you think about site C and A? Are they having same moisture level or different moisture? Same. So this is let's say block 1. This is block 2, block 3, block 4, as an example, right? And here within the block, we maintain the homogeneity, right? Within the block, we maintain the homogeneity. Between the block, what do we maintain? We maintain the heterogeneity. Within the block, we maintain the homogeneity. Between the block, heterogeneity. How many, so this is if you are doing a field experiment. How many of you are attached to animal science department? Are animal science? How the animal science igana ganna?
Yes, sir.
Sri Tivakarana. Yes, Tivakaran, tell me one example where we can do blocking in animal science. Where we can come up with a blocking. Sri Divakaran, chalo, Oma terinja chalo. Tell what will, yeah.
They consume the diet.
Consume? I couldn't hear Sri Divakaran. Chalo.
The weight and breed. The weight
right.
also vary.
Yeah, we can block breed. We can block breed. I mean, breed blocking is not very difficult approach because already breed is there. Now I am going to take only one breed. What is the prominent breed that can grow in Kilnochi? What is the prominent breed that can you grow Frisian?
No, sir.
No.
Cross
Tell me.
otherwise indigenous.
Cross with what? Which
Jersey
cross?
cross.
European
cross.
and European and Indian cross will survive, right?
Yes.
Right. So let's take Frisian and Indian cross. So we have Frisian and Indian cross, maybe the first generation, not the second or third generation. Let's say first generation, we have 15 cows, milking cows. Right. Now, I'm going to apply 5 treatments. These are hormonal treatment to induce the milk yield. Right. Now we don't have that much of cows, so anyhow I have obtained 15 cows of milking cows. At present they are milking cows of these 2 breed. I mean crossbreed, Frisian and I'm not sure Frisian will it work in Frisian. I'm not sure. Maybe Aisha or I'm not sure. Frisian, does it work? Aisha or maybe other European breed might work, right? Jersey or Aisha. I'm not sure about the Frisian, right? Anyhow, we will take this as an example. So now we cannot, even though we get 15 cows on milking stage of the same breed, we cannot get all the cows to be in the same weight, right? Because all depends on the weight also. The amount of feed that eats is totally depend on the weight of the cow. So what is the problem? So we will have the values. Let's say one is 120 kilo, the other one is 132 kilo, 155 kilo, 160 kilo, 162 kilos. Likewise, all 15 cows are there. I have put in ascending order. Now what we will have to do, we'll have to block this. After putting into ascending order, we can block first 5 cows. So this is block 1. Why? Here I'll have to give 5 treatment now, so that I need 5 animals. Then second one is called as block 2. So how many animals coming for each block?
5.
5 animals. So this is one way that you can. So likewise, we can do the blocking in different aspects. Animals, plants, trees, fields, etc., etc. Right. So here in the blocking, actually, we have one more additional component in the Anoa, right? How do you call that? That is block effect. So this is the additional component, block effect. So these 3 components will appear in the Anoa table. Right, in the Anoa table, you will get as a source of variance, treatment, block, error, and total. I'm just recalling what you have done. Nah? So here you have all these are the 3 main components. Total is actually split among these 3. So you have done already. I have seen your notes. So you have already done. Right? Then you interpret in such a way. Right. Then the next one, you have learned about Latin square design. So you see, you started with CRD, then RCBD, then Latin square design. So it goes on a hierarchy. So this is the basic design. CRD is the basic design. Little advanced one is RCBD. Further advanced one is LSD, Latin square design. Further advanced design, I will be talking in the next few classes. Not today, but a few classes, right? So these are design. But don't forget that even for your final year research, you'll have to choose the, right? Choose the simple and appropriate experimental design. So this is the important message for everyone. Choose the simple and appropriate design. So when you want to do blocking, if by knowing that you need to do the blocking, without doing blocking or RCBD, if you try to do CRD, then that is wrong design. When you want to do, if there's no reason for blocking, if there's no gradient, we call it as gradient, right? From one direction to the other gradient, moisture gradient, nutrient gradient, slope gradient. So if there's no gradient, then we cannot block it. Sometimes you need to go for CRD, but sometimes people, they fascinated to do the RCBD blocking. So that is also not good. So we'll have to choose the design according to the need and the appropriateness. So that is more important. Appropriate and the simple design. Right? Right. So you have learned the Latin square design, right? Latin square design, usually you use it in animals, right? You have three components here: mu plus, let's say, alpha I, beta j, and gamma k, as an example, plus the error. So this is how it comes for Anoa table. So these components will represent the Anoa table. These are two common terms. So this is the grand mean, this is the observed value. Each observed value split it into these components. Right? Latin square design. So you have learned about Latin square design. In Latin square design, there's a bit of problem. If you have three treatment, we have a bit of problem. What is the problem? Anyone? Latin square usually applied to a situation when you have more than equal 4 treatment. I will write it other way. When you have more than or equal 4 treatment and less than or equal 8 treatment, usually 8 or 9 depends. Why this condition is there? In Latin square, we have a condition. We cannot use for the smaller number of treatment and the higher number of treatment. Why? Anyone? Sri Tivagaran? If there's a 3 treatment, why Latin square is not good? Rania?
Experiment
Yeah.
error is reduced.
Yeah, error is Yeah, you are partially correct. Error is reduced, correct? Is the error is reduced or? Yeah. What is happening here? What is the treatment degrees of freedom? What is the total degrees of freedom? Anyone? If there's 3 treatments?
Eight.
Yeah. T square minus 1, 8. What is the treatment degrees of freedom? 2. Row degrees of freedom is 2. Column degrees of freedom 2. Therefore, 8 minus 6 is 2. So you see, error degrees of freedom is very low. If error degree of freedom is very low, what will happen to error variance or error mean square? What will happen to error mean square? What will happen to error mean square if the error degrees of freedom is low? Rania? Peony?
Is high.
Error degrees of freedom will go up. If error degrees of freedom go up, what will happen to our experiment? I explained a little earlier. What will happen if the error degrees of freedom goes up? Vidusha? Still my problem. Huh? In Trinco, always my problem is there. Huh? Okay. Anyone?
If calculated value will reduce.
If calculated value goes down, right? If calculated value will goes down, that means what is the ultimate problem? We may have more chance to not reject, or we have less chance to reject it, even though there's a treatment effect. So this is the same problem that we have come across. So this is the problem. When you have less degrees of freedom for error in the experiment, this is one of the problems. So that is why the replication also will have to be careful. We said principle of experimental design. The replication will have to have at least some level of replication. Otherwise, it will be a problem. So ultimately, it will affect the error degrees of freedom. Overall, it will affect our calculated value. To avoid that, we'll have to have more replication. So here also, the same problem. Right. What is the other problem? I said that if the treatment is 10, if the treatment is 10, what is the problem? If the treatment is 10, what is the problem? So if the treatment is 10, let's say you draw it nicely. I don't have much time to explain. You will have, you see, how many squares do you have? If the treatment is 10, how many squares you have? Uh, 100 squares. So you will end up with 100 squares like this. So what is the problem? If you consider here and here, for example, you cannot maintain the homogeneity. That is a problem, right? Here we cannot maintain the homogeneity. So that this is a biggest problem among the experimental unit. Right. So that's all principally what you have learned, because that we need for our continuation. Today, suppose if I have two treatments in CRD, can you comment on this before we go to our topic today? Two treatment in CRD. What is that? Two treatment in CRD. Anyone? If I say anyone can answer. Otherwise, I'll have to call the name. Induyalini. Two treatment in CRD. What do you think? Okay, Induyalini? Okay. I couldn't hear Induyalini.
Yes, sir.
Yeah, two treatment in CRD design. How we can call this? Anyone? Tarshani? Navaratna?
Yes, sir.
Yeah, tell me, have you learned this two treatment before? Where did you learn this two treatment? At least? We want to compare these two treatments. What is the technique available? You learn this.
Two sample t-test.
Exactly. Two sample t-test.
T-test.
But specifically, what sample? What two sample? Dependent or independent?
Dependent.
Nah, dependent when it can't be dependent. Why you say dependent? Why it is dependent?
Independent.
Independent, because treatment 1, treatment 2, two different population. This is independent. How do you call this? Pool t-test. We learned this in our previous course. So in pool t-test, we have two treatment, two groups. Suppose if you have more than two groups, what to do? Let's say T1, T2, T3. More than two groups. If it is two groups, of course, we can go for t-test, pool t-test. If it is more than two groups, what to do? Where we want to go for, right? We can go for t-test, T1 versus T2. T1 versus T3. T2 versus T3. Isn't it? This is again t-test. One time, second time, and third time. So what we are doing, using our ANOVA, we try to address this. ANOVA is applied when you have more than two treatment, independent treatment. All right? When you have more than two treatment only, we go for ANOVA. So that is how the ANOVA came into picture. If you have more than two treatment, 3, 4, 5, 6 treatment. If you have, let's say, 10 treatment, how many pairs of comparison that you'll have to do? So likewise, T1 versus T2, T1 versus T3. So how many pairs are there?
5.
Pardon? How many pairs are there?
45.
Exactly. So that is with this formula, total number of comparison. So 10 into 9, sorry, T is 10 here. We have 10 minus 1 divided by 2. So this is 45 number of times that you'll have to compare. Will it possible to compare all 45 times? Where this Anoa, we are using the Anoa table, right? So that is a part of it. Then you will learn the other part of it when you learn your mean separation technique, right? That is how the Anoa came into picture, right? Okay. I'm going to talk about a topic called as factorial experiments. Right, the title you could see factorial experiment, because I'm not going to show all the slide here. This is I have prepared this slide for master program, master of statistics, so that I cannot give all the information to you because it is too much. So whenever necessary, I will just give you the real stuff, right? So factorial experiments. The title is called as factorial experiment. Let's talk about what is this factorial experiment. My topic, first topic is factorial experiment. Right? What is the purpose of doing? I'm just introducing this lectures. What is the purpose? Right? So the purpose is combining more than or equal to more than 2 factors. Combining more than 2 factors. Let's take an example. Right, I'm taking example in agriculture. So this is my experiment. We decide, right? I will say we decide W1, W2. So I have taken 2 we decide, right? I have taken 2 we decide, W1, W2. Right, we decide. The other component is variety. Let's say V1 and V2. Let's say paddy variety or any variety. Paddy variety. And we decide. Now, I'm going to take only one we decide at a time. Let's say this is variety 1, variety 2 on a scale. Now, I want to measure their yield, response. I'm going to measure the yield, average yield of paddy. for variety 1 and variety 2. So here I have used we decide 1. Here I have used we decide 2. Right? So I'll finish this and then come to that. Right. Let's say for we decide 1, I got a high yield from variety 1 and low yield relatively to variety 2. So that this is my straight line. Similarly, I got low yield for variety 1 and high yield for variety 2 under the second we decide or we decide 2, W2. Right? Clear? So this is experiment 1. This is experiment 2. I have 2 experiments. Experiment 1 and experiment 2. So one experiment is I'm applying we decide to 2 type of varieties. The other experiment is I'm applying another type of we decide to the same variety of paddy. Indujalini, Pulangicha?
Yes, sir.
Yeah. So we apply 2 different we decide at 2 different situations. But we are applying for the same variety, same paddy variety. We are doing it as a 2 experiments. Now, we can combine these 2 experiments, right? We can combine these 2 experiments, right? Here, if you combine these 2 experiments, I will again go back to the same line. Let's say this is V1, this is V2. As an example, I am just overlaying these 2 maps. Now tell me, this black color line, average yield again, of the same variety 1 and variety 2. Black color one belongs to what we decide? Black color line?
We decide 2.
We decide 2. Am I right? Black color one, we decide 2. Right, okay. Black color is we decide 2. I will write as we decide 2. Blue color line is belongs to we decide 1. So this is what I am going to do using factorial experiment. Combining the experiments. That doesn't mean you can combine all the experiments, but that is the basic purpose and the principle of factorial experiments. So no notes, you'll have to write your own notes. So we are combining the experiments. Actually, this here, again taking we decide is called as factor. We decide is called as factor, and also variety also called as factor. We need to identify these 2. No? We decide is one factor, variety is another factor. So I say factor A is we decide, factor B is variety. Because just giving the name factor will not work, because we want to identify, right? So we decide is factor A, variety is factor B. How many we decides are there? How many VD sites are there? Anyone? How many VD sites are there?
2.
Two. What are those? W1 and W2. 2 VD sites are there. Similarly, how many varieties are there? V1 and V2. In this example, you can have any variety, any VD site, right? Any variety and any VD sites are possible. And Nelum, okay, go.
Sir.
Mic off karan.
Okay. Sorry, sir. Sorry, sir.
Okay. Factor A, VD site. Factor B, variety. Okay. So VD site has 2 type of VD site. Variety has again 2 types. So this is called as, this level is called as, sorry. This level is called as factor. This is called as levels. Factor and the levels. For example, let's say I have factor A. We usually indicate as A0, A1. Factor B, we indicate 2 levels, B0 and B1. Right? We may have several levels. That is up to us, depend on how we are doing our research. So here, factor A has, in the first case, how many levels in factor A? In first case, how many levels in factor A? Hello?
2.
2
2
levels.
levels.
2 levels. How many levels in factor B in case 1? How many levels in
2.
factor B in first case? Yes, 2. So 2 levels, so that we can write 2 to the power 2. This is indicating the levels. This is indicating the factor. So this is, we can write it, this is only for if the levels are equal. What about second case? If the levels are equal for each factor?
No, 3 and 2.
No. A has 3 levels. B has 2 levels. So this called as 2 to the power 2. In first case, it is called as 2 to the power 2 treatment combination. Treatment combination. So treatment combination, 2 to the power 2, what is that? What is the answer for 2 to the power 2?
4.
4. There are 4 treatment combinations. So I say, what are the combination? Tell me among these. A0 with B0 is one combination. A0 with B1, another combination. A1 with B0 is another combination. And what is the last combination? A1 with P1. So there are 4 treatment combinations. Hereafter, if I say TC, treatment combination. Similarly, here, how many treatment combination? Can you just tell me how many treatment combination for the second case? 3 into 2, treatment combination. So that means 6 treatment combination. Tell me what are the 6 treatment combination? Anyone? A naught, B naught, A1, sorry, A naught, B1, A naught, B2. Sorry, other way around. A naught, B naught, A naught, B1, A1, B naught, A1, B1, A2, B naught, A2, B1. All combinations, all possible combinations. So this is called as treatment combination. Yeah. So here we cannot put power, because I said power comes when the levels are same. When the levels are same, we can put it in the power. If the levels are not same, we cannot put in the power. This is also same. 2 into 2. 2 factors, right? First factor is the level of the first factor, level of the second factor. Here, level of the first factor, level of the second factor. Treatment combination. Right? Now, right. You see, coming back to this concept. Right? We said the purpose of factorial is combining the experiments, 2 experiments or 2 factors in an experiment. Combining 2 factors in an experiment. The other important aspect is, write down, this is the most important, to investigate the interaction. I will explain this little later. So this is the hardcore of factorial experiments, to investigate interaction. Right? Hardcore of the factorial experiment. So when you combine these 2 factors, we can give the, we can go for and see whether the interaction is there. Right? Right? So without combining these 2, we decide experiment, as I shown you. First we decide, second we decide. If you apply separately in a 2 different experiment, then we cannot talk about this interaction. Okay. Okay. So we will define what is this interaction in few minutes. Right. Maybe I will take some glass of water, some hot water, and come. Give me 3 minutes. We can have 3 minutes break. I will get a cup of water. Okay, we can continue. Are you all there?
Yes, sir.
Okay, right. So the purpose of factorial is to obtain to investigate the interactions, right? So when you talk about interaction, I mean, I just go for some introduction on the factorial, which I have as a PowerPoint presentation. Let's can you all see the slide? Yes?
Yes, sir.
Yes, sir.
Right, okay. So here, the factorial experiment, some notes, right? Intervention studies of two or more categorical explanatory variable, which I said these are the factors, right? Leading to a numerical outcome variables are called as factorial design, right? Intervention studies with two or more categorical variable. A factor is a simply categorical variable, right? You know, categorical grouping variable with two or more values referred to as levels. So this is what I have already defined as the factor and the level. So we can have any factors, any number of factors, any number of levels, right? A study in which there are three factors with two levels. So all three factors are having same level, two levels each. Then we can say 2 to the power 3 factorial design. So this is how we call as 2 to the power 3 factorial design. Right? 2 to the power 3 factorial design. So this is what I have already explained to you. If you have factor A and factor B, each of them have equal levels, A1, A2, or B1, B2 for factor B. So you can give any names, A0, A1, or A1, A2, doesn't matter, right? If blocking has been used, it is counted as one of the factor, right? So if there's a blocking between factors, so that it is basically called as factors, one factor, right? In the field, blocking we have already talked about. Blocking helps to improve the precision and the raising the homogeneity of the response. What are the advantage of factorial experiment? We didn't define the interaction yet, right? What is the advantage of factorial experiment? So the advantage of the factorial experiment, first one is, it is giving a greater precision can be obtained estimating the overall main effects. That is one of the advantage. The reason is, write down this, I will explain in detail. The reason, there are hidden replicates. There are hidden replicates, right? The other advantage is interaction between different factors can be explored. So this is what I said already, interaction. Normally, this is the main objective of factorial. This is the main objective of the factorial, right? The estimation of the main factor overall main effect is secondary, right? So the interaction is the most important. Additional factors can be helped to extend the validity of the conclusion derived. So this is another advantage. Additional factors can be helpful in extending their validity of the conclusion. Right, look at here, just to explain the same thing which I have already explained to you, right? Let's say you have two factors. One is factor A, the other one is factor B. These are two levels, right? Can you remember we said already factor, if you say factor A naught and A1, factor B, B naught and B1. Usually, if you take levels, these two levels of a single factor are basically called as lower level and the upper level. Lower level, and this is upper level. Usually, that is how it takes place. Lower level and the upper level. So here, you understand what is meant by lower level, B lower level and the B upper level. B lower level mean B naught, B upper higher level mean B1. So here, this is A naught and the A1. As an example, some value. I'm going to show you some value, just to talk about the interaction. I'm going to explain the interactions. What do you mean by interaction? We already said we are combining the experiments so that it is called as factorial. So the main purpose of this factorial is to look after the interaction of the experiment. Look at this. If I plot it like as I did already, we decide two types of we decide, varieties, two types of varieties or two varieties, right? Right. If you just plot these values, A low and A high, B low and B high. So here A low and A high, this is factor A, B low and B high, this is factor B. Explaining factor B, these are observations. Some values, yield or whatever, the response basically. We can say response. That is what we measure. Right? Is it clear? Right. Now I didn't do anything. I have just drawn their values. According to that, it says more or less a parallel line as an example. Now tell me, in this case, if I take this as a variety 1, this as variety 2, this as we decide 2, and we decide 1. Now, an early example, I take variety 1 and variety 2. Tell me, what is the best we decide for variety 1? What is the best we decide for variety 1? Subhangi?
So according to previous one, we decide 1 is good. According to this, we decide 2.
No. Now I am asking now.
2. W2.
Yeah. So for variety 1, we decide 2 is good. Am I right? I'm asking now, not previous. I'm asking now. So now, what is the good we decide for variety 1? So the answer is we decide 2. Again, the same question, little differently. What is the good we decide for variety 2? What is the good we decide or the best we decide for variety 2 to obtain the high yield? Our main aim is to obtain in the high yield.
It also W2.
W2. So for variety 1 also, you have, we decide 2 is the best we decide. We are using only 2 we decide, W1 and W2, not the other in the experiment. So variety 2 also, for variety 2 also, the same we decide is the good. So that kind of situation called as no interaction. Write down very carefully. No interaction means, for example, in this case, it is more or less parallel. So that no interaction at all. Okay? No interaction at all. Right, let's look at the second scenario. I have another example, the same condition. Right, now look at this. Again, we go for the same variety, right? Variety 1, variety 2. So below what we said, is it we decide 1 or 2? I couldn't remember. Earlier, in the earlier slide, what we said for below, is it W1 or W2?
W1. W1.
W1, this is W2. Okay, thank you. Right, now tell me, for variety 1, which we decide is good. Compare these two.
We decide 2.
We decide 2 is good for variety 1. Similarly, for variety 2, which we decide is good.
We decide 1.
We decide 1. So this you see, for one variety, 1 we decide is good. For the next variety, not the same we decide. Some other we decide is good. So this phenomena is called as interaction. So how we can define the interaction? I will go back to define the interaction. Sorry, pressing something else. So how we can explain the interaction? Response of level of one factor is if the response of level of one factor is different from the response of level of other factor. If the response of level of one factor is different from the response level of other factor, then it is called as presence of interaction. Presence of interaction. So this is how we define. The response of the level of one factor is different from the response of the level of another factor. So that it is called as interaction. So carefully read this and compare with the example which I showed. Right? So we have no interaction and there's an interaction. Right, now let's say I have a factor A. You have two levels, A0, A1. Factor B, B0, B1. Let's say this is A is variety, B is spacing. I'm doing a trial for spacing and variety. Do you think all the varieties having same spacing or different spacing of a single crop? What do you think? Spacing, it depends on what of a crop?
Canopy.
Yes, canopy. Basically canopy and the how the roots will be spread out. Right? So that let's say A is a variety, B is a spacing. We have two spacing, doesn't matter. You understand? Right? So what are the combination? A0, B1, or B0, A0, B1, A1, B0, A1, B1. Do you agree with that?
Yes.
So yeah, this is called as treatment combination. How many treatment combinations are there? 4 treatment combinations. Now, these are the one that is going to be tested. These are the treatments. Here in the factorial, we don't call it as treatment. We call it as treatment combination. Why? Because it is combined of different levels of each factor. Right? So here, factorial is factorial experiment is the arrangement of treatment. It is not the design. Some people are misusing the term called as factorial is not a design. It is a treatment arrangement. Now, what are the treatment arrangement in our case? A0, B0 is 1. A0, B1 is the second one. A1, B0 and A1, B1. So 4 treatment combinations. Now let's say, now these are the ones which we call as our treatment. Now let's say I have a RCBD, right? 3 replicate. So this is block 1. This is block 2. Block 3. Right? What do you mean by block size? In RCBD, block size. What do you mean by block size? In RCBD, block size is equal to what? Here in this example, what is the block size? How many blocks are there? That you can see directly. How many blocks are there?
12.
No, I'm asking how many blocks are there?
3.
3 blocks. So this is block 1, block 2, block 3. What you said, 12, what is that? 12 mean, what is that? How many?
Units,
Experimental units. How many experimental units? Or you can call it as how many plots. If you are laying out in the field, it is how many experimental units, total number of experimental units, or total number of plots. That is 12. What I ask is block size. Block size.
Spacing
Shoe
of the-
size. Let's say shoe size. Shoe size mean, what is that? How many shoes you have? Normally, how many shoes do you wear?
a pair.
A pair. When I ask shoe size, is it the size of one shoe or two shoes?
Both
Huh?
shoes in same size.
Both shoes same size, but I'm asking, when you buy in the shop, what is your shoe size mean? Dekam ekatu karala again.
No.
That is the question that I ask. When you ask the shoe size, what do you say? It is the size of one single shoe. So when you say block size, can you tell me what is the block size now? It is a size of one single block. Anyone?
Spacing of the
Not spacing.
Or experimental units.
4 experimental units. So block size means number of experimental units in a single block. Number of experimental units in a single block. How many experimental units are there in a single block in this case?
4.
4. This is block size. Because this block size is very important. That is why RCBD. What is the meaning of C here? Yeah, complete. So forget about the factorial now. Let's say I have 4 treatments. T1, T2, T3, T4. So now tell me, what is the relationship between block size and the number of treatment? I have only 4 treatments. It has some name. I have 4 treatments named as A, B, C, D. So this is one arrangement. The other arrangement is this. I have 4 treatments. This is one type of arrangement. This is another type of arrangement. Tell me, what is the difference between these two? Sabiba, what is the difference between those two?
block size different.
Block size different. What else? One, you can say block size different. This is First situation, second situation. Block size is different. Good.
In each block, the externals are evenly distributed. Same.
Where?
First one, the four treatments, 4 types of treatments are equally provided for each block.
Okay. Second one?
Second one, not equally.
Right. So here, usually block size we indicate as K. Block size we indicate as K is equal to what in case number 1? Anyone? 4, but technically tell, yeah, it is true.
A plus B plus.
Yeah, how do you call that? Block size is equal to what? I'm talking about RCBD now, huh? Just because we need to talk about RCBD also. Yeah. Block size is equal, block size we give as K is equal to what? Can somebody tell me?
C into B.
Is that correct? Can I write like this in first case? Block size is equal to what?
Total number of treatment.
Yes, number of treatment. Total number of treatment. So we give it as treatment, total number of treatment as T. What is happening here? Which one is higher here? This is case number 2.
C treatment.
One treatment for each block is missing.
One treatment for each block is missing. So that is fine. D is missing here, A is missing there, and B is missing there in these 3 blocks. Now, how we can talk about this relationship? Which one is higher? Is this equal? Simple mathematics. Is this equal? Is the K equal to T?
No.
No. What is K here?
Block.
Yeah, what is K here? I need the numerical value. What is K here? What is the value of K? This is the single block. This is single block. So what is the block size? K is the block size. Huh? I couldn't. Yes? Tarshani?
3.
3. Yes. Right? So how we can write this? We can say, can I write like this? Yes or no?
Yes.
Yes. So here, this is complete. This is called as incomplete. So complete means all the treatments are present in a single block. So that is RCBD. All the treatments are present in a single block. That is called as complete. Incomplete means all the treatments are not present in a single block. So there are different types of incomplete. If you come to master level, we will learn it. So this is a condition called as incomplete. So there are designs based on this that we are not going to learn in this course. Complete, we learn always complete. So that is why RCBD, randomized complete block design. So all the treatments are present in a single block. So that is called as complete. Right? Okay. Right. So this is nothing to do with our problem, but anyhow, you should know. Right? You should know some of the concept of complete and incomplete. Right. Coming back now, all the treatments, if I want to accommodate all the treatment combinations, for example, A naught, B naught, A naught, B1, A1, B naught, A1, B1. So all the treatment combinations are present here. So this is how we arrange the treatment combination in a block, if it is a RCBD. So here, this kind of design, I can call it as how many factors are there? We said one is variety, the other one is spacing. How many factors are there? 2 factors, right? So that we can say this experiment, the variety and the, what do you call, variety and spacing. So this experiment, variety and spacing experiment, we called as 2-factor factorial in RCBD. So this is how we put the title of the design, 2-factor factorial in RCBD. So everybody understand there are 2 factors. The design is RCBD. Similarly, we can do 2-factor factorial in CRD. 2-factor factorial in CRD. That is also possible. Right? 2-factor factorial in RCBD, 2-factor factorial in CRD. We will look at the type of model and then Anoa, etc. later, but we will understand a little more further on this aspects, right? So we already talked about interaction, which I showed you the interaction, right? This is no interaction. This is with interaction. Okay. Normally, if it is 2 levels, if it is 2 levels, if it is 3 levels, it is complicated. If it is 2 levels, let's say you have first factor, you have second factor. Because 2 levels, we set A naught and A1, for example. So we say this is minus, this is plus, right? Similarly, 2 levels of factor B, this is minus, this is plus. This is factor A, this is factor B. Right? Factor A and factor B. Right? So this is what we are going to explain. For example, here A naught, B naught, A1, A naught, B1. A1 B naught, A1 B1. How can we represent this? Anyone? How we can say A naught and B naught here according to this sign? Tell me. Yeah.
Negative, negative.
Yeah, these two are negative. Second one, negative and positive, positive and negative, positive and positive. You see, we have just given the coding. That's all. Right. Look at here. Here also we are doing a coding like this for a 2 into 2 factor levels. Right. So here this is A naught, B naught, A1, B naught, A naught, B1, A1, B1. So this is called as combination, treatment combination. Now, if you have 3 factors, let's say A naught, B naught, sorry, A naught, A1, factor B, B naught, B1, factor C, C naught, C1. So how many combinations are there? Can somebody tell me how many total combinations are there? 2 to the power 3 combinations. These are the levels, these are the factors. So altogether we have 8 combinations. You see, 8 combinations are there. If you have 3 factors, likewise 4 factors, 5 factors, 6 factors, we can move. We are not going to learn about more than 3 factors here, right? 3 factor mean if you have each factor with same level as 2, then total combination is 6 combination, 8 combination. So this is how, for example, this is A naught, B naught, C naught. This is A1, B naught, C naught. So likewise, you can write for each of these combinations. So 8 combinations are there. Any questions? Today we may go till 5:30. Don't worry. Anybody has any urgent work? Maybe some of you have already. Yeah, I see almost everybody is there. Batch rep?
Yes, sir, I'm here.
No. Any urgency of finishing the class?
No, sir.
Right. Okay, good.
Up to 5:30, okay, sir. 6 p.m. the special class is there.
Pardon? 5:30?
Up to 5:30, okay, sir.
6 o'clock you have another class?
Yes, sir.
Okay, right. Okay. I will leave at 5:30, yes. Because we have started so that breaking in the middle, I mean, you don't get any benefit out of it. Okay, right. So the factorial setup is same. You have minimum 2 factors should be there. You can have 3, 4, and so on. But we don't go for large factor factorial. We will learn that if you come to postgraduate institute, then we can learn about large factor factorial. But basically, we in this course maximum 3. 3 factors, right? Right. How to the setup actually in the factorial setup, right? We said, for example, the setup is we said factor A naught A1, factor B naught B1. So we have effects. Effects due to factor A. That means between these two. Effects due to factor B, that is between difference between those two. And the effects between these two which is called as interaction. So these are the three effects that we can come across in this case. For example, if you have A, B, C, I have three factors. What are the effects possible? Can you list out what are the effects possible? If I have A, B, C. Darshani?
Effect of A,
Yeah.
B,
B.
C,
Good.
A into B,
Good.
A into C,
Good.
B into C,
Good.
A into B into C.
Excellent. So you see, this is how we write down the effects. So this is, all these are called as interaction. So you see here, we had two factor in earlier case. So these are called as main effects. Main effects. So main effects A, main effect A. Similarly, we call it as main effect. I'll put it as ME, main effect B. And this is interaction effect of AB. I hope everybody is writing down. Huh? So this is main effect A, main effect B, interaction effect of AB. Similarly, this is main effect of A, main effect of B, and main effect of E. See. Now you see, these are interactions. These are interactions. These interaction also we can divide into groups. The first group of interaction, this is called as two-way interaction. Two-way interaction. This is two-way interaction or two-order interaction. This is called as three-way interaction or three-way interaction or higher order interaction. Why higher? We say higher order interaction because that is the maximum order that we can get, A, B, C. So here also we can say it is two-way interaction or higher order interaction. Two-way interaction or higher order interaction. That is also possible. Right? Is it clear? Any questions? Right. Now, let's say I have A, B, C, D. Write down main effects. What are the main effects? A, B, C, D. What are the two-way interaction? Can somebody tell me what are the two-way interactions? How many two-way interactions are there? Rosha? Yeah. Write down. Tell me what are those?
AB,
Yeah.
AC,
Hmm.
AD,
Hmm.
and BC, BD,
Hmm.
last one CD.
Okay, good. Right. What about three-way interaction? How many three-way interactions are there? How many three-way interactions are there? Anyone?
ABC, ABD, ACD,
Just a second. A, B, C.
ABD, ACD, BCD.
Okay, good. What about the highest order or the last one? This is called as four-way or highest order interaction. So A, B, C, D. You see how complicated when you have four factor. You see so many effects. 4 effects, 6 effects, 4 effects, again 1 effect. Almost 15 effects. You see. So this is a real challenge actually. If you have 4 factor, 5 factor, 6 factor, we don't go detail into 4, 5 factors. We maximum stop with 3 factors. All right. So these are called as interactions and the main effects. So everybody knows what is main effect and the interaction. Now I'm going to talk a little on these effects. Right. So let's say I have only 2 factors. Suppose I have only 2 factors, right? Or right, when I come to example, I will go for the 2 factors. As I pointed out, we go for main effects. We go for evaluation of main effects. Suppose if I want to evaluate the main effect of A, right? How I evaluate the main effect of A? Yield when the treatment is high. So that means average yield of A1 minus average yield of A0 in according to my explanation. A0 and A1 are the 2 levels. So the high level minus the lower level. So that is how we find out the effects of main effects. In other words, we can say average response of when X is equal, whatever the level, maybe it is the higher level, and minus when X equal lower level. Average response when the X equal the lower level. That is how we find out the values. This is just an example, right? So these are the response. For example, tell me this is A0, B0, A1, B0, A0, B1, A1, B1. They are response values. If I want to compare X1, main effect of X1, see where the plus values are of the main effects. What are the plus values of the main effects? What are the plus values? Sorry, main effect of X1 here. So this is one, right? This is the other one. So average of 5 plus 8 divided by 2. So minus, take the average of minus value, that is 14 and 30. 14 plus 3, not 13, divided by 2. So this will get a negative value. So this is how we calculate the main effects. Is it clear? So we consider only this. Right? Okay. X1 main effects. We get the values of this. Similarly, we can calculate the main effect of sorry. Can you repeat previous one, sir? Yeah, which one you want to repeat? Previous and the previous. Previous, right. So here, forget about these values, or just let's say I have A, I will consider it as A, factor of A and factor of B. A naught, B naught, A naught, B1, A1, B naught, A1, B1. So this is how it goes, combination. All right. So here, if I want to find out main effect, I will put it as ME, main effect of A. How we can say? Average of A1 minus average of A naught. Do you all agree? Average, because I am talking about only A, average of A1 minus average of A naught. So let's say here we have values some 10, 15, 20, 25 as an example. Now average of A1. What is the average of A1? 20 plus 25 divided by 2 minus average of A naught. What is that? 10 plus 15 divided by 2. Yeah. Is this understandable? Person who asked this question? Right. Right. So average of this could be given as such, right? We can write down as such, right? So this is, tell me main effect of B, how we calculate the main effect of B? Tell me in the numbers. I need in the numbers, sir. Main effect of B. Anyone? If you tell only, we will move. Otherwise, we will stop here. We will stuck here, not stop. Very quickly. Anyone?
15 plus 25.
Yes, 15 plus 25 divided by 2 minus
10 plus 20 divided by
10 plus 20, yes, divided by 2. So this is a simple aspect, right? So the principle is important. Huh? Average of B1 minus average of B naught. Oh, basically, we look at the difference. We look at the difference, absolute difference. Not necessary to have higher to lower value, but absolute difference. If the absolute difference is higher and higher and higher, there's a difference. Right. We will go back to interaction. Sorry. If you want to look at the interaction, sorry. Where did I stop? Very quickly, Going back the interaction, this is the main effect. Interaction is not given here. Right, now interaction, sorry. How to look at the interaction here? What to do? We want to find out the interaction. That is more important, isn't it? So we can plot and see. Oh, if you want to calculate the interaction, A into B, anyone suggest how we can calculate? Anyone? Yeah.
If we compare the both main effect,
Both main effects, yeah.
where the effect is high, here their interaction is
Right.
high.
So, okay, right, good. Anyhow, your thought is good. Here, when you talk about interaction, now we can remember this is minus or plus. A naught is minus or plus.
Minus.
Minus. This is minus. I will use a red pen. Huh? I will take another 5 minutes. Huh? This is minus. What about B naught? Minus. This is minus. This is plus. This is plus. This is minus. This is plus. This is minus. Now, tell me what is the product of minus into minus?
Plus.
Plus. What is the product of minus into minus? Sorry, minus into plus.
Minus.
What is the product of plus into minus?
Plus minus.
I have done something wrong. No? This is plus. Do you understand the principle? Do you understand the principle here? Minus into minus is plus. So this is plus. Minus into plus is minus. Plus into minus is minus. Plus into plus is again plus. So now you see interaction calculation. Interaction calculation, right? I will calculate the interaction is the average of pluses, that is 10 plus 25 divided by 2, the difference. Huh? The average of minuses, 15 plus 20 divided by 2. So this is the concept of interaction. This is different from earlier. This concept is different from earlier on. You don't get this earlier, right? In earlier calculation, you don't get this. So the interaction calculation is slightly different. So easy to show by calculation for this. Right, I think since you all have other classes at 6 o'clock, we can stop at this point, we will continue. So I could have given the whole lecture in 2 hours, but everybody should understand. So that is. Is it clear up to now, pathway? Blangita? Yes? Blangita though? Anush Kumar? Blangita?
Oh, yes.
Okay. Padilida? Patagaraputika Padilida? Other?
Oh, sir.
Oh, right. Then I think we will wind up and continue. Still, by probably next class, we would be able to complete this. I'm not sure, but we can, because I'm going slowly. Not.
Sir, excuse me.
Hello.
Sir.
Yeah.
Sir, புதன்கிழமை தானே சார் போட்டீங்க, நாளைக்கு இல்ல தானே கிளாஸ்?
இல்ல 29 காலை 8 மணிக்கு.
ஓகே சார், அப்ப நாளைக்கு. ஓகே சார், தேங்க்யூ.
நாளைக்கு 28 தானே? Yeah, so I have placed my next class on 29th at 8 o'clock. 29th at 8 o'clock. Huh?
Yes, sir. Yes.
அது பிரச்சனை இல்லை தானே மெட்டாக்களுக்கு?
இல்ல சார், இல்ல.
Right. Okay. Thank you. Then see you on Wednesday.
Thank you,
Right.
sir.
Bye. Bye.
Bye.